Okay, one more quick bonus example. I said I wasn't going to do this, but I'm going to try it anyway. Which is to show you the way I learned to do these problems back in the day when I was taking Physics 2, which is a little bit different than the way your book does it. And there are things I like better about it, and things that are harder. The good thing about it is instead of getting 3 equations with 3 unknowns, you get 2 equations with 2 unknowns. And the way you do that is you don't use the junction rule. You just define the current loops the way you want them, and then you take care of the places where the loops overlap. So if we do the same example again, I'm just going to define one current, I1, that goes around this loop that way, and another current, I2, that goes around this loop that way. No I3. In the places here where the 2 currents overlap, I will take into account that the current flowing through this loop is I1 plus I2. Okay, I1 this way, I2 this way, that way. And I will use that as my current when I go through that 48 ohm resistor. So in some sense what you're doing is you're taking that junction rule into account manually rather than giving it its own equation. So let's imagine I did my 2 loops. I start here, I go around the top loop, I go around the bottom loop. What would that give me? If I start here in this circuit, I go through a 9-volt battery, potential difference of 9 volts. The current through this 25 ohm resistor is I1, so there's a potential drop of I1 times 25 ohms. Then I go through the 48 ohm resistor, so there's a potential drop of the current times 48 ohms. What is the current through that resistor? It's I1 plus I2. Okay. Then I get back home again to where I started, and so my total potential difference around the loop is 0. So that gives me one equation that says 9 volts minus, I'll throw my ohms away, 25 I1 minus 48 I1 minus 48 I2 equals 0. Or if I prefer, I can combine those terms together, and I get, what's 25 plus 48? 25 plus 48 is 73. I get 73 I1 plus 48 I2 equals 9. Okay, so there's one of my equations. Everything's got a negative sign, and move the 9 volts to the other side. It has a positive sign. Now do my other loop. I'm going to start here. Well, it's a little confusing if I start there. Well, I'm going to start here and I'm going to go around the loop that way. So the first thing I encounter is the 12-volt battery. I'm going from negative to positive, so that's an increase in electric potential, 12 volts. Then I go through this 35 ohm resistor, so there's going to be a voltage drop of I2 times 35 ohms. Then I go through the 48 ohm resistor, so there's a potential drop of that current times 48 ohms. Where that current, again, I'm going with I2 and I1 together, so that current is I1 plus I2. And then I get back to where I started, so the total potential drop is 0. So I've got 12 volts minus 35 I2 minus 48 I1 minus 48 I2 equals 0. And that gives me, what have I got here? I've got 48 I1 plus 35 plus 48. Oops. 35 plus 48. 83 I2 equals 12. Let me check my signs. I1 is negative, I2 is negative, 35 plus 48 is 83, 12 goes to the other side, becomes negative, divide through by negative 1, everything's positive. So notice that now, instead of having 3 equations and 3 unknowns. I've got 2 equations and 2 unknowns, and that's a heck of a lot easier to solve algebraically than the other ones were. In fact, it's tempting to actually do this myself rather than rely on Wolfram Alpha to do it. But just to save time, let's go to Wolfram Alpha and have it solve the system of simultaneous equations for me. My system of simultaneous equations is 73I1, so that's 73x, plus 48I2 equals 9, and 48I1 plus 83I2 equals 12. Wolfram Alpha will solve that exactly and give us some fractions. I will ask for it in approximate form so I don't have to do the math myself. And what do I get? I get x, which is I1, is 0.045. 0.0455, let's say that's 0.046. And y equals 0.118, that's I2, equals 0.12 amps. So these are the currents we get from that solution, which tells us that the current here, I1, is 0.046 amps that away. The current here, I2, is 0.12 amps that way. And the current here in the middle is the sum of those two, where those two currents overlap, which would be 0.166 amps that way. And if we compare that to the answer we got last time, 0.046, 0.12, 0.16, 0.046 that way, 16 this way, 12 that way, 046, 16, 12 that way. So it checks out. I like this method because it gives you one fewer set of equations to solve. This can be super ugly if your loops are going in the wrong direction, or if you chose the wrong direction, if you're going upstream instead. This can be confusing, taking care of that place where the currents overlap. It can get more confusing in problems with a higher number of loops. We haven't looked at any of those yet, but suppose I gave you a circuit that looked like this. Battery, battery, resistor, 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 resistor. Sure, that's probably plenty. See, this is a 9-volt battery, and this is a 5-volt battery. Say this is 3 ohms, 4 ohms, 5 ohms, 2 ohms. How would I solve a problem like that using Kirchhoff's rules? I've got a certain current through here, a certain current through here. The current splits here and goes this way and this way. And then when it hits here, it splits again and goes this way and this way. So I've got, if I call this I1, I2, I3, I4, I5 to all keep track of. I4 is here, I5 is here. We get back to I1 there. I could have as many as 4 equations and 4 unknowns are here with five equations and 5 unknowns. The number of currents goes up with the number of loops. So these problems can actually get really, really complicated. So the way I just showed you how to do it, instead of having 5 different currents, you would have one current I1, one current I2, one current I3, a current for each loop instead of a current for each segment. That decreases the number of simultaneous equations you have to solve. But you have to be careful here. in this part of the circuit, you've got I1 going this way, I2 going that way. The current is equal to I1 minus I2. Here in this part of the circuit, we've got I2 and I3 overlapping. The current is equal to, if you're going this way, I2 minus I3. It can get kind of ugly, and it can be easy, again, easy to make sign mistakes with all of these different versions of the problem. I don't think I'm going to give you a 3-loop Kirchhoff's rule problem to solve. I don't even think I'm going to give an example of one. I'd rather just do some simple 2-loop problems, practice them, and get the heck out of this chapter while we still can. We're running out of time. So that, if you like this other alternative method, this is the way, I think it's the way my old Halliday and Resnick physics textbook does it. It'd be interesting to look at the new version of Halliday and Resnick and see if they still do it the old way or the new way. Like I said, it's all about keeping track of the different amounts of current in the different loops, and there are different ways to do that. But if you do everything right, you should always get the right answer in the end.